said he tried it. Tanishka said tried. Based on what Shreya mentioned, do you guys feel like you could approach this now?
Yes.
Okay. So main idea is really not about getting surprised with all these points. It is just noticing which of the points are actually behaving according to the description of bill given above. So you could actually conveniently choose, I think, like the first 2 points, because this one gives you just one equation in one variable, right? Because when you use 0 units, you really just get the fixed daily rate. So you could get one equation out of this point, one more equation out of this point. So let's just see. So the first equation would be, so starting with 30D, so we would have like 30D equal to 0.72. That's our first equation, because that's the first point, right? Where you use 0 units, but you still have some bill. Then the second equation is 30D plus R1 equal to 0.84. You could pick any other point in this range between 1 to 394 units, because all of them are, I said it's more like a linear charge, because I'm saying, how do you get 30D? Because that's the fixed monthly charges, right? Monthly fixed charges are 30 times my daily charges. I just said, like, for ease of working with these numbers, you could use that, right? So that's the fixed cost. Then you could use any one of these points and pick these. So same way you continue. If you pick any point that's greater than 394, let's say we pick this one, which is 10 more units than 394. So you get 30D plus 394 times R1 plus 10 times R2. Let me see if I can remember the syntax. Okay, does this do any good? Okay. Okay, so these are the 3 equations. So I can even now do this way. Right, they are all linear functions. Yes. Why are we using 3 equations? Because there are 4 variables, right? We are not done yet. There are 4 variables. There is a variable D, which is the daily charge. And then, yeah, we are supposed to. We haven't gotten there yet. So somebody paused in between. Then you have some point like this one, which is more than 1572. Something, this one. So this is going to give me like a whole number, ending in 0. Actually, not whole number. All of them will give me whole number. So where was I? So my last equation is 30D plus 394 times R1 plus 1182 times R2 plus 80 times R3. This one, what was the cost here? 49.9. This one, the cost is 293.38. So we got 4 equations and we have 4 variables. Hope you can see my screen and see these 4 equations. Oops, I missed somewhere. Okay, so 4 equations, 4 variables. You should be able to solve this, right? Now, what is the matrix for this? So if you want to solve this in one shot, what Shreya did is also fine. You could actually just solve the first 2 equations, then start plugging in. Yeah, sure. This is the system of equations. What is the matrix form of this system of linear equations? How do you convert, or what is the coefficient matrix, and what is the variable matrix for this one? Okay. Is anyone trying to type? If we have no, so that's the advantage of a linear equation, right? Like as long as you picked 4 points that fell in that ranges, 1 point for 0 units, or even if you don't pick the 0 units, it doesn't matter. You could pick any points in the right range and write the right equation. So let's pick 4 other points. So let me take these 2 points, okay, 14, 17. That's why it is a linear equation, right? Because if not, this would be some other kind of equation where the point would have made all the difference. And let's pick this number and the last number, right? The equations that you would get here are 30D plus 14R1 equal to 2.4, and 30D plus 17R1 equal to 2.76, and 30D plus 394R1 plus 221R2 equal to 89.99. Then finally 30D plus 394R1 plus 1182R2 plus what was the number, 1576. So 24 plus 392, 416 equal to 380.74. Okay, so these could be 2 sets of equations. So let me right. So this you could get 2 sets of equations. Actually, just for the sake of looking at the solution, let's see if we plug in both sets of equations. Let's see if we get the same answer. How do you get 1182? I think I mentioned here in the problem already, right? Like, so the way I'm charged is if my electricity usage is more than 1576 kilowatt hours, for the first 394 kilowatt hours, I'm paying at R1. Next 1182 kilowatt hours, I'm paying at R2. And the remaining I'm paying at R3, right? So that's in the question itself. That's how the bill is. Actually, this is exactly how my electricity bill is. So I just opened my electricity bill and gave you the numbers. So okay. So now let's write the corresponding matrices, and just to see if both of them result in the same thing. How many of you think they will give the same answer versus they'll give me different answers depending on the equation? So let's see. A little different if real life data. This is actually real life data, Shruti. As I said, it's exactly what my electricity bill formula is. Can you share this collab? Yeah, after I'm done typing. So the first equation was 30. So from the first equation, what is the from the first set of equation, what is the matrix equivalent, or like what are the coefficients for all the 4 variables in the first equation? Zero for the remaining 3, right? Like, so 30, 0, 0. So 30, 0, 0, 0, right? So for the first set, the equation starts with something like this, 30, 0, 0, 0. And then you have, I think this is the syntax is begin matrix, maybe B matrix. Let's see, and the B matrix. Does it look like a matrix? Yeah, it looks like a matrix. Okay. So for the first one, it is 30, 0, 0, or 30 and 3 zeros. For the second equation, what's the matrix equivalent? For this second equation, what's the, if you are representing 30, 1, 0, 0, okay. For the third equation, what's the equivalent? Okay, perfect. 30, 394, 10. And for the last one, obviously, all of you know by now what we are doing. I think I missed something so that it would give me proper spacing, but let me see if I do this. Does it give me good spacing? Yeah, I forgot the syntax for how we are supposed to type this one. So I'm probably getting this looking very badly. Yeah, looks like I made some mistake in some syntax. Maybe I'm supposed to do it this way. Let me try. Yeah, I think I'm supposed to do it this way. So that it looks nicer. The reason I'm making it look nicer is not so that it looks good, but also because I want to show something about this matrix. Okay, so this is the matrix representation of the first one, right? So I'll just copy these things, put it in the equation thing that I was about to type. So here I need to replace all the ampersands with commas. Oh, is it doing it here? Yeah, okay. Okay, I don't want to do it there. And then I replace each of these with okay, so that's my A for the first one. What is my cost equation? That's the right hand side. So that's 0.72, 0.84, oops, 49.9, and oh, I deleted the 80. Yeah, sorry. Thank you. 289, 293.38. Hopefully I did that right. So let's just see, just in case I made some mistakes so that I can compare easily. Okay, 31, 30, 00, 31, 00, 394, 10. Okay, looks correct. Okay, so now how do you solve this? So how do we solve this? What is B doing? B is like the cost. So these are the costs, right? 0.8, 0.72, 0.84, 0.9, 49.9. Those are the costs for various points. So now how do you solve this? Okay, inverse of the coefficient matrix. How do you calculate inverse of the coefficient matrix? Okay, np dot linalg dot inverse. Is that inverse or inv? It's just inv. Okay, now let's print our A inverse. Okay, np. Oh, not Lee. Typing mistake. Okay, so it gave some inverse, right? So whatever it represents, it gave some inverse. And then finally, what is our solution? NP dot of A inverse comma B, right? Okay, and then let's print this X. So we got some solution that says this is our costs, right? 24.024 and 0.12, 0.19, 0.26. So the actual program is really simple. Finds product. Yeah, we'll come to what does it do. Okay. So now let's try with the second set. So the second set, the coefficients were 30, 14, 30, 17, 30, 394, 221, and 416. And the costs were 2.4, 2.76, 89.99, and 380.74. Okay, so let's try this one. So we got exactly the same solution, right? So this is what we were trying to do. Now, of course, if you plot this thing, as I mentioned here, so let's just copy this one and plot this. Plug in these values, 0.024, 0.12. If anyone has the code for this, give it to me so that I don't spend time typing it all up here. Okay. Yeah, okay, let's copy this one. Okay. Indentation. Okay, R1 times quantity. Can probably do this. We wouldn't do anything wrong, so let's ignore that you did it wrong. Okay, so is this all right? Okay, so 394 R1, 1182 R2, okay, 1576 R3. Okay, perfect. So we just pick all this and then we'll plot. Oops, can't assign literal. Commas don't work. Okay. Okay, so do we have a plot? Yeah, we have a plot, right? So if you notice, there are, like Shreya mentioned, this is a piecewise linear function. So why is this interesting? And not because it shows us some plot of something, but if you notice, is this a question just to find the? No, the question is also to plot. And I think that's what the question had. So you're supposed to plot as well. Plot the amount of units and bill. Okay. So what we had originally started off with was, when we started last class, we thought we'll solve like just linear equations, right? But what you saw here is using the same style of representing system of equations with matrices, you can also solve piecewise linear equations under right constraints, right? Of course, you can't solve any equation with this method, but certain type you can definitely solve with this method. Even when it is not like fully linear, even when it is piecewise linear, same method works. So that's why this method is powerful. And why is that interesting? Not so much for the class, but a little bit in real life, because in real life, irrespective of the function of the relationship between input and output, you can oftentimes approximate in certain regions that relationship with straight lines. That's why linear algebra is so popular amongst computational statistics, or amongst computational fields. The linear algebra is extremely well used because of this reason, because you could approximate even a crazy looking function with linear approximations. How many of you know how area of a circle was found out? Do you know how area of a circle was found out originally? Yeah, I know pi r squared, but how did they find out pi r squared? They measured it using rulers. Yeah, actually very close. They didn't measure it using rulers, but yeah, kind of, not exactly. So what Archimedes did, they wrapped a string around it and measured the string. Very difficult. No, they didn't do that. So what they did is Archimedes. Let me see if I can find a nice diagram that illustrates this. No. Okay, yeah, this right, this method. It's called method of exhaustion. But what they did is they started with one circle, put a square inside it, then put an octagon inside it, then put a what is this called? Hex dodecagon?
A
I don't know.
double hexagon. It has 16
No, it's
sides.
16, right? No, it's probably like
I'm
some
not
hex.
sure of the real name, but it has 16 sides.
Yeah, absolutely. Yeah, 16 gone. So they kept going like this, I think up to 80 something gone, and then or 96 gone. Yeah, hexadecagon. Okay, cool. So hexadecagon. They went up to hexananogon. Some mathman did 96 sides. Yeah, the name of that mathman is Archimedes, I think. Yeah. No, Google gone and all is not needed. So once you do that many gons, you really can't actually distinguish it from a circle. Even at n equal to 16, if you notice the red line and the blue lines are almost merging everywhere, right? Oh, really? It's called that? Wow, I did not know that. Okay, cool. So as you can see, that's how they have been doing it for 2000 years. They didn't really calculate area of a circle directly. They approximated it with linear approximations and calculated it. So about 2000 years, people have been doing the same trick, and it still works. So that's why linear algebra is so much in fashion even after all these years. Okay, so that's the storytelling part and the homework part. So now in last class, when we looked at solving linear equations, described it more, at least for the two-dimensional linear equation solving, as like 2 points intersecting with the 2 lines, the intersection point of 2 lines, right? It doesn't. Can you share this collab? Yeah, I can share this collab. Okay. It's a 999 sided polygon. Okay, I don't know why that is an important thing for us, but yeah. So let's see, continuing on. So last class when we saw this intuition of geometric representation of what solving a linear equation, system of linear equations in 2 variables was, our way of saying was it's the point of intersection of 2 lines. So let's take this first homework problem and just try to see if that. So let's clear all this. Okay, so 2x minus 9y equal to 14. Actually, you guys probably solved this one also, right? So you already saw x plus 6y equal to 7. Right, so we said these are like 2 linear equations and they meet at some point, and that's the solution of a system of linear equations. This intuition is fine, but this doesn't really this is not how current state of linear algebra was approached. This intuition of thinking of them as the solution of where 2 lines intersect is absolutely fine. There is nothing wrong. But what is not really great about this intuition is it's not just 2 equations. It's not just 2 equations that pass through this point. You could create a ton of equations that pass through this point, right? So why were those 2 equations so special? There's nothing special about those 2 equations, right? You could probably, can you tell me some other equations? So some 2x plus 7y equal to 14. That also passes through that point, right? So it's not doing that much justice to what this really solving a system of 2 linear equations means. So in this class, we'll look at a slightly different way of thinking of why these matrices come about in solving linear equations. What we have done so far is understanding how to represent, given a system of linear equations, how to represent that in matrix form and how to solve this. But what we are trying to do today is like why to solve it this way. So delete all this. I did it not delete everything. Okay, anyways. So all of you are familiar with solving linear equations in one dimension, right? Like if I just give you one variable, 4y equal to 16, you know how to solve that, right? So when 4y equal to 16, what is y? 4. Okay, perfect. So let's just start with that. So we say y equal to 4 comma 0, so that it nicely draws for me. And if I say 4, this made it a u. Okay. So if you can see here, when we say 4y, it's simply just like a stretched version of the point, right? We started with this point 4 comma 0 or 4. I'm imagining, because this is one dimension, you can think of this as a number line. So we started at a point 4 and then stretched it. But a point is just a point, right? Yeah, the idea of vector, yeah, right. So, but it's not really, you can't stretch a point, right? Because a point is just a simple dot. You can't really, it has no dimension, you can't stretch a point. So the intuition is really you are taking the arrow from 0 to 4, this line, which is from 0 to 4, and then stretching it 4 times. That's the intuition. When you, it's a quantity with a magnitude and direction like an arrow. Exactly. And a vector is just on the number line. A vector is simply the line that connects origin to a given point on the number line. On a 2D plane also, it's exactly the same thing. You can think of these vectors that we are talking about. In general, if you take any line and draw it in some direction and some length, that's a vector. So you can think of a vector as a line, that's all. A line segment, actually, to be more, well, actually a vector is a line segment. So that's what it is. But in this case specifically, we are focused on the vector that connects origin to our point of interest, right? So that's a special kind of vector. We'll still keep calling it vector. That's it, no big deal, right? So we are taking this vector and stretching it. We could also do things like stretch it and add something to this vector, right? This one is not very friendly. So we could add something to our vector, which will make it so will this thing. So now if you notice, this is our vector. After stretched, it is pushed a little bit, right? So some vector. When we say solving a linear equation in one variable, what we are really doing is we know this longer vector and we are trying to find the original vector. Of course, all of this should be straightforward to you guys. This is how you did, like from second grade or third grade, whenever you started multiplying two numbers and adding a number to it. This is all the same stuff, nothing fancy, but we are just using the word vector. So we have this stretched and pushed. So this is stretching. I'm calling this as stretching because we took this 4, we did it 4 times. And then I'm saying this is pushing. So we have a stretched and pushed version of this vector. And we want to find out what is the original one. Why are we interested in this? Because sometimes this is all you can observe. So let's say, for example, you are observing the shadow of something. You can observe the shadow, but maybe you can't observe the object that is casting that shadow. From the shadow, can you find out the height of the object? Is that something you can find out?
Yes.
Absolutely. And this is the practice that has been there for thousands of years. And what have they been using this for? Shadows for finding something?
They triangulated, I think.
Not really, but have you heard of any place where they use shadows to find something? Sundial, yeah, absolutely. Yeah, right. Sundial. So for a long time, people used sundials to find out what's the time of the day, right? You would use the shadow. So this is a good sundial. So you'd use the shadow, and that shadow tells you what time of the day is. So Basically some idea, basically just to say, okay, hey, you can use something that is like a transformed version of the original. So this is the transformed version of the original. You can use this to mean something, right? Like the time is the original one and the transformed version of the time is the shadow, and you could use that to actually go back and find out the time. Makes sense? Roughly. So when we say we are trying to solve a linear equation in one variable, this is what we are doing. We have a stretched and pushed version. What can you do in one dimension? Like when you have only the number line, what are the things you can do with this vector, with this starting vector? You can stretch it, you can push it. What else can you do? Squish it. Okay, so you can squish it. What would be the equivalent of squishing it? So you could say something like u divided by 3. So this a is the squished version of u. Okay, u divided by 4. Let's change that to u divided by 4. Okay, so that's the squished version of it. Break it. No, we don't want to break things. We want to just keep things smooth. Dividing, subtracting. So what would subtracting be? More like pulling it, right? Like you're pushing it or pulling it or stretching it or squishing it, right? Can you do anything else? Delete, break, all those things are like damaging it. Without damaging it, what can you do? No difference in this way, but stretching is like your, well, actually there is a difference, right? Like if you're pushing, you push in steps. When you're stretching, you just keep on, you do it in one smooth action. So what in mathematical terms, stretching is multiplication, pushing is addition. Raise it to nth power, but that's the same as like stretching it for a long time, right? Take the nth root, again, same kind of idea. Right, in terms of actions we can do, these are the only 4 actions. You can increase its length or decrease its length. Change direction. Okay, nice. So change direction. If you multiply it with a negative number, you can change direction. So that's a good one. So let's say minus 2u. So now it's change direction, right? Well, we are talking in one dimension, right? At this point, we are simply talking in one dimension. So number line. So you could stretch it in the opposite direction. That's what really we could do, right? So these are the operations you can do. Now, when we talk about two-dimensional equations or yeah. So this is all in one dimension. Is this intuition clear to you guys? Like, hope this is not something new that I have introduced, but this is the basic intuition in one dimension, right? You start with a point or you start with a vector, you're stretching it, pushing it, squishing it or pulling it, whatever, and that gives you a final vector. If somebody only tells you the final vector and they told you how they got there, you can reverse the operations and find out the original vector, right? That's the general idea. Hopefully that is clear. So this is how you solve linear equations in one variable. Nothing really complicated there, hopefully. Is it not clear to someone? Because we'll use this in the next step. Okay, glad it is clear to everyone. So now let's start with another vector in 2 dimensions, right? It is a bit confusing. Vidyut, what is confusing? Yeah, that's what I want to know. Vidyut, when you say it's confusing, what is confusing? Because I want you to have that clear picture so that we can proceed and discuss this in 2 dimensions also. Right, exactly. What Prince is saying is right. Like, so if somebody tells me my vector is at 19, like my vector is 19 comma 0, and what I did to get there is I took an initial vector. It's a single dimension if it's a number, not a pair, right? Yeah, you can think of it as a single dimension. Because I'm plotting here on a 2-dimensional chart, I'm having to think of it as 14 comma 0. So let's say my initial point is something I don't know. We started at 19 or we are ended at 19, and somebody tells me, okay, I ended at 19, but that was because I took That was because I took a given initial vector and I stretched it 4 times. What is vector? Vector is this arrow with you, that's all. Vector is the arrow that joins origin to that point. How do you solve it? How do you solve it if I say, okay, I took a initial vector of some place and I stretched it 4 times. So if I tell you how to solve 4u plus 3 equal to 19, how do you solve it? You're not solving the vector, you're taking the final vector and bringing it, reversing the steps to come back to the initial vector. That's what solving is really. I gave you 2 vectors, these 2 things, right? I gave you these 2 vectors. Right, so I've given you this 2 vectors. Yeah, 4u plus 3 equal to 19. Yes, that's what I said, because that's what I did, right? So I said 4u plus 3 gave me 19. So if I tell you I have this bigger vector, what I did to get here is I took an initial starting vector, stretched it 4 times, then pushed it 3 times, or multiplied it with 4 and added 3, and I got here. So you know how to solve this, right? Okay, cool. So this is the intuition. We know the longer vector, we want to come back to the original vector. So you reverse the operations. Because in 2 dimensions, there are only, in 1 dimension, there is only either multiplication, addition, subtraction, division. In all along this line, it's relatively easy to change these, reverse the order of operations that resulted in this. But what if we tried in 3 dimensions? So let's say somehow I did this, and so if you notice, this was my starting vector u. Let's add some more things to this. Do you see my starting vector is u and this is my resulting vector v? Does this make sense? Same thing in 2 dimension, nothing different, right? What same exact idea what we tried in 1 dimension in 2 dimension. So now I'm given this 2-dimensional vector. I'm supposed to find out this starting 2-dimensional vector. So if I'm given the arrow v, and if I'm told, okay, this is the operations that I did to get it here, then I should be able to find this. Does that make sense? Right. So this is the general idea. You start from this 2-dimensional vector and you try to land at this, you start at this transform. I'm multiplying by 2. Yeah, actually, what is the 3, 4 doing? I am taking this vector, initial one. So let's do it in steps. So I'm taking this initial vector and stretching it 4 times, right? 4u is just stretching it 4 times. Then I'm I'm shifting it a little bit. I'm taking this 4 times u1 and I'm turning it a little bit. You could think of it, yeah, transformation. So this is the idea of a linear transformation. So what did I do in this transformation? I started out, I stretched them, and then I'm rotating in some direction, right? Does this make sense? So in 2 dimensions, what are the operations I can do? Kind of, right? Like I started here and I rotated it a little bit. Is this along the same line? My u and w are not along the same line, right? U was in this direction, this is in this direction. So I rotated it a little bit. What is the difference between 1-dimensional and 2-dimensional? 1 dimension, would the u be the point where the vector starts? Okay, so first question, what is the difference? There is no difference between a 1-dimensional vector and 2-dimensional. What is the difference between number line and plane and 3-dimension? What is the difference between 2-dimension and 3-dimension? Shirish Goel. What is the difference between 2-dimension and 3-dimension? Right. Yeah. So basically, there is really no difference between 1-dimensional vector to 2-dimensional vector. The idea is the same. A vector is whatever line that connects, in our case, in this instance, whatever line that connects the origin to that point of interest, that's a vector. If the point of interest, if our whole world was in 1 dimension, then it's a 1-dimensional vector. If our point of interest is in on the xy plane, then it's a 2-dimensional vector. If our point of interest is in an xyz plane, then it's a 3-dimensional vector, right? So that's it. Nothing. There is no difference. It's still irrespective of the dimension. It is still the line that joins origin to our point of interest. That's the vector that we are interested in. Would u be the point where the vector starts? So with it, u is not the point where the vector starts. U is the vector's name. That's also just the name of that vector instead of giving it some other name. So this is u. We took this vector and then we stretched it and rotated it a little bit, right? Does this make sense? Okay. Now in 2 dimensions, what are the operations that you can do? In 1 dimension, you could do a few. In 2 dimensions, what is the number 4 and 1 in the first one doing? Okay, Vidyut, tell me, have you studied like planes or like two dimensions in school? So how do you represent a point on an xy plane? Four comma one, right? That's all I did. This thing is just printing it like this. So I typed 4 comma 1, and for sure, for showing it, it's showing to me in linear in that fashion. Right? Yes, Prince. That's what I'm doing. I'm adding 3 and 4 to different points, but the effective result is rotation, right? Like, because I'm not adding the same thing to both. Even if I would have added same thing to both. Oops, what happened? Interesting, something went wrong. Let's delete and start. Okay, so u equal to 4 comma 1, then v equal to 4u plus. See, adding this has the interesting effect of rotation, right? Adding the extra points has the effect of rotation. And why is this happening? We'll see a little bit on why is this happening. There are actually very good YouTube videos. You can watch those to get a better intuition for what is happening here. But this is our starting vector. We stretched it and turned it a little bit. When you add some number to x coordinate, and when you add another number to y coordinate, the effect is turning it a little bit. Does that make sense? It's because we are adding the same thing to each point, so it looks, even if you add different things, it looks like it is moved, right? So if I add a 1 comma 1 4, it will still look like it's moved. How does it become 19 comma 7? So okay, Vidyut, take a point 4 comma 1 and multiply it with 4. Where does that point land? So let's take this one. Let's just do this part. So we took a point 4 comma 1 and we multiplied with 4. It landed at 16 comma 4, right? So because you are stretching it in that direction. So you took this, you stretched it, it went to 16 comma 4. Then I'm adding 3 to each direction. So let's say first I add only 3 to one direction. If you noticed, it's just a little bit off in that direction. And then if I add another 3 to this, it's in the slightly different direction, right? So adding numbers to this has a result of rotating them. Okay. This is still in standard position of a vector, right? Yeah, because the vectors that are not, the initial point is not. Yeah, this is there are different things that refer to them in different ways. You can, yeah, you can think of it as standard position of a vector, absolutely. Yeah, but right, for our purposes, a vector is anything that connects a given point to the origin. So that's what our definition of a vector is. In some places, they would call it specially and say standard position of a vector, but in most linear algebra conversations, that is kind of understood. Like there is no other vector other than the one that starts from origin. Okay, so this is our starting point. Now we have this. When we say solve the equation, what we want to figure out is, okay, given that we have done these transformations and arrived here, what was the starting point? But how do you describe these transformations? Before we do, how do we describe these transformations? Why is 4, 1 there if the initial value isn't 4, 1? Vidyut, when did I say initial value isn't 4, 1? Initial point is not 0, 0 in Shruti's question. She's asking, this is called standard position of a vector or whatever point she's referring to. When you call a vector as the one that starts at 0, 0, right, yeah, I don't want to overload with terms because there is no other, in our definition, you start at origin, draw a line to a point, that's a vector. You can use 20 other words for that, but it's the idea that is important. Don't get lost in the words. The idea is, I drew an arrow, then I stretched it, rotated it. That's the idea. Focus on the idea. Don't worry too much about the words and the letters and the directions and the arrows. Think about the idea. We are not trying to worry about definitions, okay? Because based on last few minutes of questions, that's what it looks like. It is becoming more of why. Is the idea clear? We started with a line, stretched it and turned it. That's the whole point. Does that make sense? Okay. So given that transformation, what other transformations can you do without breaking the vector? What other transformations could you think of doing in 2 dimensions if we had to do in this? So starting from a line, what else can you do to a line? Squish it, okay. What else can you think of doing? You could do all the things you did now, except now you could do it to X or Y, okay. Yeah, the one thing you couldn't do in 2 dimensions was 1 dimension was rotating, right? Like in 1 dimension, there was really no rotation. Maybe there was like a mirror image, but there was no rotation. So you couldn't take it from the number line and push it out of the number line. So that wasn't there. That's there a little bit here. Rotation, reflection, yeah. So you could do an extra thing. Now, when we were doing in 1 dimension, multiplying something was like stretching it or scaling it. Adding something to it was pushing it. But in 2 dimensions, as you can see, adding even a number has some interesting impact of like rotation. So the way to look at this is basically, let me see if I can do this in Paint. So let's say we start with a axis like this. This is our initial arrow. Instead of thinking we are rotating the arrow or we are stretching the arrow, I can think as if the sheet itself has been stretched, right? If the sheet on which this was drawn, like imagine you drew it on some polythene paper or like a plastic paper and you stretched it evenly on all directions, then automatically this line that you drew with these points would actually become bigger, right? Because now it would, oops, didn't mean to do that way, but right, that's one way to think of it. Does it make sense? One way to think of scaling is you're not scaling the individual vector, but you're scaling the paper on which you drew it. you're stretching it, right? Then rotation, you can think of as if this initial axis itself has been rotated a little bit. So if you do this now, this vector would be somewhere here, right? Right, like x rotations, y rotations, whatever, right? Yeah. So now this is my new x-axis. Let me see if I draw it in a different color, it may be more. So rotation is something like this, right? I take, oops. So under this rotation of this axis, this should be somewhere here. I'm probably drawing it very poorly, but this is the idea, right? So given this, so I've basically described, okay, I stretched my sheet 4 times on both the directions, right? 4 times stretch. So initially I stretched it 4 times on both the directions. Then I added 3 to both the directions. So let's say that's what my new result is. So that took my initial vector and it put me in this kind of a position, right? Oops. Does this make sense? Okay. So when we say we are solving linear equations in 2 dimensions, what we are trying to find out is, given these stretches and rotations, what was my initial vector? So that's the way in which we can think of solving linear equations in 2 variables. That's another way. Our previous intuition was 2 lines, like the point where 2 lines met. That's not a bad way of thinking about it. This is another way of thinking about it, which makes more the linear algebra thing better, come more realistic or be more clear. So what you can, is this the entire series of transformations? Like you can do millions of transformations like this, right? Like you can keep rotating, turning, twisting, whatever you want to do. As long as you don't tear the paper or you don't break this, you can come up with any sort of transformations. That's why, of course, you have lots of equations. However, how to best describe all these equations in one style, right? That was the focus of how matrices came out to be. As you already saw in the previous way of looking at this, when you had these equations, some 2x plus 3y equal to 4, so vector have to, not in our context, right? In our context, vector always is the line that starts from 0, 0 and goes to that point. You can obviously push it, but you're always only pushing this part. Let's say that's what we are defining, so that we don't have to worry about some other problems or other interesting things. So in our context, that's what we are describing. But yeah, of course, in real life, you could also push from the origin also. You can do origin translation as well. Actually, that's a good point, because I think that's what I did not do here. Oh, okay, I'll do it later. So when we saw like linear equations like this, we already know that it doesn't matter what the variable names are. We can reduce this to like 4 numbers and 2 numbers. So the 4 numbers on the left hand side and the 2 numbers on the right hand side, and that will uniquely identify the point. So with that idea in mind, that's the same thing that you could do even with this kind of a transformation. The way you think about it is, for all linear transformations, I'm taking a starting point. Let's say I'm taking this as my starting point. I'll use a different color. So this green arrow is my starting point. This is just the vector 1, 1, right? It's just 1, 1. If I know what happens to my vector 1, 1 after all these transformations, so my initial vector is 1, 1. If I know where my initial vector's x value ends up being and where my y value ends up being, I claim that I have given that equation, or then I can take any vector and find out what's its resulting position. Does this make sense? Because that's how we are saying we'll describe the transformations. We'll describe the transformations as if they have happened to our initial vector. What are the endpoints of our initial vector 1, 1, or our unit vector? What are the endpoints of our unit vector 1, 1 after the transformations? And then I'll apply that to the vector of interest to get the final one. That's our goal. So our unit vector, let's say u, is 1, 1, or without the arrow. If I know what happens to this u, so let's say it becomes u hat, then I can say for any given vector x, I can apply the same transformation and get x hat. So this is x hat and this is x in our terminology. And this is u, this green line is u. So because it's a linear transformation, right? Like because you're stretching the paper, whatever line you had initially drawn, let's say you had 4 lines, hat is just, okay, you can call it anything else. U becomes new u. Okay, that may be a better way to think of it. Just some notation. Transformed version, it's just a standard notation for transformed version, but we can call it u becomes a, x becomes b. Okay, some letter basically to represent the same thing. So if u becomes a, then x becomes b under the same transformation, right? Because if you had 2 lines drawn on the original paper, after rotation, both those 2 lines will end up at 2 different places, right? Like they would have also changed. So the way to represent these transformations is by saying, okay, where does my point 1, 1 end? So if my point 1, 1, let's say, for example, the x coordinate of this under the new transformation. So initially it was here. So let's say under the new transformation, it ends here. So whatever is the position of the x on this one, and whatever is the where the point 1 landed, and where the x value of point 1 and the y value of point 1, where did they land? Relative to that, that's roughly going to give us where the new position of everything is going to be. So the way they describe that is in this example that I wrote above. So I can say like my 1 starts here, and this is the place it ends up at 2, 3, and my other one starts here and it ends up at 3, 4. And this will be my new position, whatever this one. So this will be my new position for my 1, 1. It will be at 5, 7. Because this is the effect of my transformation. My initial one ended up at 2, 3 after this transformation. My one on the x-axis here, because even this is composed of 2 vectors, right? So this one here and this one here. These 2 arrows ended up being somewhere here now. This arrow is here and this arrow is here, right? Or sorry, not there. This arrow is here along these red lines. So if you notice, my initial arrow, which was along this 1, 0, now is ending up somewhere here, right? And my unit vector, which was along 0, 1, ended up somewhere here. So I'm taking these 2 positions and saying that's where this ended up, 2, 3, and this probably ended up at, let's say, -1, 4. So this is my resulting position of 1, 7. So my unit vector ended up at 1, 7 because my unit vectors x component and y component ended up being at these places. Does this make sense? Okay. If it is not clear to someone, let me know, and I'll maybe like describe it slightly in a different way if I can. Okay, so let me draw this on a new one so that I can. So I initially started off. So to describe my transformation, what I'm claiming is, instead of describing some numbers, what I could say is I can tell you this is my unit vectors on my initial plane, right? These are my unit vectors. So this is point 1, 0. This is point 0, 1. So these are my unit vectors. Unit just because they are one unit on the y-axis, one unit on the x-axis, right? So this is my initial unit vectors. After I do my two operations, which is stretching. So when I stretched it, my unit vectors also got stretched, right? So let's say this became 0, 4 and 4, 0, right? Because I'm saying I'm stretching it in the same amount in both directions. There is no need to stretch it in the same amount in both directions. So is this clear? So I stretched it, and what was initially this point went to these two places now. Does that make sense? Okay. So now I'm going to rotate my axis and say I'm going to rotate this way. Sorry, missed it. Not very good at drawing in paint, but okay, so somewhat very close. Now where does this blue line go when I rotated it? It obviously still sticking to this line, so I rotated it and it went here, and this blue line that was here ends up, let's say, being here. Right? So my unit vector started at being this. From here, after the transformation, they ended up at this point and this point. That's where my unit vectors ended up being. Does that make sense? Yeah. So if you want to look at this in normal two-dimensional coordinates, what would the position of this be? So what is this position roughly? So if this was 4, 0, so let's say this is 4, 3. Okay, yeah, 4, 3. So I'm writing this in this order just because all of these points I will just write in this order in this instead of writing 1, 0 horizontally, I'm just writing it vertically. That notation has some advantage, which we will go later. We don't have to worry about what's the notation advantage. That's just some notation. So it shouldn't really change what I'm doing. Instead of writing them horizontally, I'm just going to write them vertically. This is 1, 0, and this is 0, 1, right? Still the same thing what you are used to in school. So this is the point 0, 1, this is the point 1, 0, but I'm just writing them vertically. That's all. So I'll delete whatever I had already started, and this should give us what we want. Oops. I should probably switch to my phone soon. That way I can draw these things without any effort. But okay, 0, 4. So where is the final point for this y unit? The unit vector along y-axis, the unit vector along x-axis ended up being at 4, 3. Where did the unit vector along y-axis end up being? Roughly, if you had to roughly guess. What would the coordinates of this point be? Minus 2, 6. Okay, it looks like that. Yeah, okay, let's just say minus 2, 6. So this ended up here. So what I'm saying is, once I know where my unit vector 1, 1 ended up, so this ended up at, let's say, this is where it would end up, right? I would draw this here and I would draw this here. And my unit vector now ended up somewhere here. Right, so this is roughly where So for those of you who know how to do this with Pythagoras formula, where is this? This is 416 root 20, and this is 36 945 root 45. So root 20, I would just say somehow like it ended up. Actually, we can just compute this like this. So to know where my unit vector ended up, what I'm claiming is I'm saying, okay, my x direction ended up here, and my y direction ended up here. No, it won't end up at 4 6, right? Because this is neither 4. So if this is 4 and this is 6, so if this is 6 and this is 4, this is not nowhere near 4 or 6, right? It's different from 4 or 6. Does that make sense, Meda? Right. So this is what I'm saying. Because my x direction one ended up at 4 3 and my y direction one ended up minus 2 6, I'm going to add up these things, and the way I would do is I will say 4 times 1, 4 times 1 plus 1 times minus 2, so that's 4 minus 2 and 3 plus 6. So I'm claiming I ended up at 2 comma 9, which roughly looks like it, right? Like this point looks like roughly about half of where we started. This point looks like it's slightly above 6, right? If this line is 6, this point looks like it's above 6, so this is ending up at 2 comma 9. Does this so far with me? So my initial unit vector here along x and y directions ended up at 4 3 and minus 2 6, and that meant my vector 1 comma 1 or 1 1 ended up at 2 9. Now if I take any other vector, so this would be, let's say this is it looks like it's 2 1 2 or maybe 0.2, so 1 2. So if I take any other vector, I'm claiming that where 1 2 ends up is the same way. So I take, to know where did 1 2 end up, I would take 1, multiply that with 4 3 and add 2 multiplied with minus 2 6. So what does this give me? This gives me 4. 1 times 4 is 4 plus 2 times minus 2 is minus 4. 1 times 3 is 3 plus 2 times 6 is 12. So this is telling me that my initial vector ended up at 0 comma 15, my vector. So whatever this red line was, after my transformations, ends up actually at a somewhat surprising. So it only has the y component. So it ends up somewhere, oops, not on this direction, but somewhere here. Can you explain how I got minus 2 6? I'm just reading off of this position, why that applies. So I'm not, after I transform this y-axis, right? So here, this point, where is this point roughly in my initial vector axis still? So if I'm assuming this is my, let me draw in some other color. So if I'm assuming this is my initial axis still, corresponding to those brown lines, where is this point? Corresponding to the brown lines, roughly. This looks like it is roughly at minus 2 and roughly at 6, right? You don't have, it is not exactly there, obviously. I don't know where it is, but it's roughly like around that. Does that make sense? My unit vector along y direction ended up being here. My unit vector along x direction ended up being here. Does that make sense? Prince Rohatgi, does that make sense? I didn't get it. I just made I'm claiming that point. Why does it work for both vectors? When you say both vectors, you're talking about why does it work for this green line and this red line? Right, because it's the same paper that I'm stretching and turning, right? Imagine this is a paper that I'm stretching and turning. I drew two lines and I stretched the paper and turned the paper. I didn't do it differently for each of the lines, right? I just did the same stretching and same rotation. So that's why whatever works for my unit vector works for any other vector in that plane. So this transformation, that's the idea, right? And of course, this is only for a certain type of transformations where I'm not tearing the paper, where I'm not bending the paper. If I do all those things, then obviously this doesn't work. This is assuming I'm not stretching, tearing, bending, whatever, just linearly pulling it, linearly rotating it. So in that style, this would work. Okay. So now the way to think of this is my unit vector 1, 1, or one way to think of it, under this transformation where 4, 3 and minus 2, 6. So what I did is I wrote the transformations of x and y coordinate together, resulted in this new vector 2, 9. Internet problem. Oh, okay. So what I'm claiming is all I need to represent this stretching and rotation of the paper is just where did my x coordinate or where did my x direction unit vector and y direction unit vector end up. That's all. So as long as I know those positions, I'm saying I can take any other line on this and I can figure out that one. So when we say matrices, that's all this is really. So the first column in the matrix is really where the x unit vector ended up. The second column in the matrix is where the y unit vector ended up. Does this roughly make sense after the transformations? Right. And we are saying by just representing these in this matrix form, I can apply this for any transformation. I can apply the same transformation for any point on this line, or sorry, any point on this initial paper or initial plane and get the resulting vector by applying the same transformation. So these set of 4 numbers are what is sufficient to describe the transformations. Does this make sense? Now this is what is really happening when we say, okay, 2x or let's say 4x minus 2y equal to 2 and 3x plus 6y equal to 9. What is happening is I'm taking the point 1, 1. When I put x equal to 1, y equal to 1, 4x minus 2y is equal to 2. When I say x equal to 1 and y equal to 1, 3x plus 6y is equal to 9. That's all, right? So that's why these linear equations in 2 variables and this matrix form are equivalent, because in both the cases, what they represent is once I take the unit vector along each axis, where does it end up? So that's how these two are connected. Obviously, this intuition did not happen overnight, right? Like people knew how to do this for a long time before they connected how to do this. This only came up about 1800s, mid 1800s. So for almost 2000 years, people never thought of these two ways as the same. In 1800s, there were like I think a French mathematician called Binot, and another British mathematician called Cayley. They both came up with this style of thinking about it. And so ever since, that's the way that's been thought of. So this is how these two are connected and why we proceed from linear equations to matrices. Now, we'll look at how to solve or why the matrix inverse is motivated. We can take a short break. You guys can come back at 11 o'clock, anyone, or 11 too. So 10-minute break, and then we'll look at what is matrix inverse, how to actually arrive at matrix inverse and why to arrive at matrix inverse. You can take a short break now, 10 minutes. Does anyone have any questions? Those of you who have questions, you can stay and ask those questions now.
How does this we apply this in coding?
You don't apply this in coding. This is how you build imagination, right? Like this is called intuition, right? So this is the intuition behind the code, right? I'm explaining how this, why
Okay.
this happens, so that when you code, you just don't type and not realize what's happening.
Okay.
Idea of taking some input point, applying a transformation and resulting point. So that's how most of at least basic machine learning algorithms operate. They apply some transformation and try to arrive at that conclusion. So you have to really have this imagination in your head when let's say linear regression model is working. That's what it's really. It's not doing this exactly, but it. You can think of some of the machine learning algorithms as in terms of this. Any other questions? Okay, I'll also take a break then. Can you guys hear me now? Okay, cool. Yeah. Yeah, I was not muted. I was disconnected. So didn't expect. Okay. Okay, cool. Okay. Yeah. So what I was trying to do basically is, yeah, I was trying to say this is what we saw so far is how linear equations can be viewed as linear transformations, and how knowing where the unit vector along x and y axis can be used to describe this matrix, which then can be used to apply the same transformation for any points. So that's how matrices came out to be. So how many of you are familiar with this notation f of x comma y equal to c? If you are not familiar, let me know if you're not familiar with what this kind of represents, f of x comma. Okay, so what this is it's like a function in two variables is equal to some constant. Okay, so the two variables is, in our case, we are writing every, okay, yeah, no problem. So it's like something like this, x square plus y square equal to 1. This can be represented as f of x comma y equal to 1, where f of x comma y is x square plus y square, right? So this is just like writing functions in two variables. So similar to that, what we are going to look at is the general form of xy plus, oh yeah, f of xy equal to xy plus x square by y, yeah, sure. Yeah, xy, well, whatever, yeah, something like that, just like a function, yes, normal function. So like this notation, what we are trying to come up with is a notation for how to represent all linear equations in two variables. So what I'm claiming is like, okay, if I write it this way, I'm saying this is my transformation, or what we were calling as A, this is my transformation, and this is my vector. This results in some new point, and this is my resulting vector v new. right? So this is the general form of representing a linear equation in two variables. Already you guys are familiar with this. Now, what does this AB represent, or what do you multiply this A and B? You multiply that with X, because that's what the unit vector in X direction had transformed to. This one goes with Y, right? So the multiplication of this is kind of like this. So you would say X times AB plus Y times, yes, AX plus CY, yes, correct. So Y times CD equal to EF. This is because the first vector, or the first column in the matrix, was what the X point ended up at. Second column is where the Y point ended up. So you get this as AX plus CY equal to, I should have written it as in the general form, which is ABCD, not ACBD, but okay, fine. AX plus CY equal to E, and BX plus DY equal to F. So this is by doing this operations in this order, where the first column is multiplied with the first value here, second column is multiplied with the second value here, and adding them up, you end up getting these equations. This is matrix vector multiplication. Does this make sense? Okay, cool. Now let's see matrix multiplication. So what we are claiming is this. This is matrix A. What if I took a paper, rotated, stretched, whatever? What is the yeah, exactly, I'm explaining that. So matrix multiplication, the purpose of it is, so when you do a matrix vector multiplication, the purpose of it is to find out where this vector xy landed under this stretching and rotation, where it landed. That's the purpose of matrix vector multiplication, to find out what is the final destination of a given point, or final landing point for a given starting point. When I say matrix multiplication, what that does is, each matrix is one set of rotating and stretching the paper, right? So you rotated the paper, you stretch the paper. That's one matrix multiplication. What if I did it 2-3 times? So first I rotated, stretched it. Then I stretched it even more and rotated it in some other direction. Does it make sense? Can I do that? Like I can start from here, right? I start with this axis, I stretch it, and then I rotate it. Then I stretch it again and rotate it completely like this. So is this possible? I mean, you can imagine this kind of thing happening, right? So that's what the purpose of matrix multiplication is. So when we are multiplying matrices, all we are doing is we are applying two transformations, one set of rotation stretching, another set of rotation stretching. That's it. So that's what matrix multiplication really represents. How do you do that is what we will look at right now. But it's no strange than the matrix vector multiplication. It's almost the same thing if you followed that matrix vector multiplication. So let's take this. So I'll write this as alpha, beta, gamma, delta. Very poor. Actually, let me switch to my phone and I'll start sharing from there. On my phone, I can do this more easily. Pawan, can you make my, like I connected with a different account on the phone. Can you make me host or co-host there? What name did I connect as? Okay, cool. Okay, let's expand this thing. Okay. So hopefully you guys can see my screen. Okay. So matrix We started with a simple matrix A, B, C, D. Multiplying this with a vector xy gives us where that xy ends up. Okay, let me see which right. So this is the purpose of matrix vector multiplication. So this is a matrix vector multiplication, and this is called as dot product. This gives us new vector position. And matrix represents the set of transformations you did, what stretch, what rotate. And once you multiply this, you know where this vector xy ended up after doing those transformations. So if you apply the same set of transformations twice, so like say A, B, C, D with alpha, beta, gamma, delta, right? So this is applying two sets of transformations. Now, how do you multiply this? So when you had vector, right? So let's say we split it like this. We say we only had one of this, alpha and gamma. What is the result if you only had A, B, C, D and alpha, gamma? What is the resulting matrix? Anyone who wants to try? So this first column multiplies with this first value, right? So alpha AC. And the second column multiplies with second value. So gamma times BD. So that gives us alpha A plus gamma B, alpha C plus gamma D. I'm writing gamma very poorly, almost like an R, but bear with me. So this is our first column in this resultant matrix, right? So because I started off here, I wanted to multiply this matrix with this matrix. I divided it into two pieces because I'm just saying, okay, I'll multiply this with this first and then this with this next. So now I'm doing A, B, C, D with beta delta. And I would just get beta times AC plus delta times BD. So that would be beta A plus delta B and beta C plus delta D. Does this make sense? I can't blame you writing the Greek letters. Yeah, my gamma. Yeah, thank you, Magna. Right. So the result of multiplying this matrix with this vector was this thing. This is our first column in the resultant one. The result of multiplying this matrix with the second one is this. This is our second column in the resultant vector. So we have this messy looking vector gamma A plus alpha A plus gamma B, alpha C plus gamma D, and then beta A plus delta B, and then beta C plus delta D. This is our resulting vector. So just so you guys see, we started with a vector that had 2 rows, 2 columns. If you multiply with a vector that has 2 rows and 1 column, what are we getting? We are getting a vector which has 2 rows and 1 column. I'm hoping that is very clear. Actually, before I go there, is this matrix multiplication kind of making sense? Okay. If anybody has questions, we can pause and check. Okay, Komal. So, Komal, do you have a question or is that not very clear? Okay, so just to check how your understanding is, 2, 3, 4, 5. What is the result of this matrix multiplication? You guys try on your side and tell me what is the result of this matrix multiplication. Okay, 10, 6. Oh, you used program to do this or you did it manually? Manual. Okay, so let's check. So that's 2 times 2, 4 plus 3 times 3, 5. right? So this first column goes with this value, second column goes with this value. So what does this give? This is 4, 8 plus 9, 15. So it's 13, 23. Right, 13, 23. So what we are saying is whatever this matrix represents, if we do the transformation, this 0.23 becomes 1323. Okay, so now let's try this multiplication. 2, 3, 4, 5 with 1, 0, 0, 1. So try this matrix multiplication and oh, actually, sorry, this is trivial. 1, 2, 3, 4. So if you multiply these two matrices, 2, 3, 4, 5 and 1, 2, 3, 4, what do you get? Okay, we can go over the matrix multiplication again. So with these numbers, what I'm doing is I'm separating this second matrix into two halves. So I'm saying when I multiply this matrix 2, 3, 4, 5 with 1, 3, what do I get? What is the result of multiplying this matrix 2, 3, 4, 5 with 1, 3? It can't be one number, right? Okay, good. Yeah. Does anyone see how this became 1119? If someone doesn't see how this became 1119, please let me know. We can pause and try. How? Okay. So Shreyan, did you follow this part where 2, 3, 4, 5 was multiplied with 2 and 3? Okay. So we took 2, 3, 4, 5. We multiplied with the 1 with 2, 4, 3 with 3, 5. 1 times 2 is 2. 3 times 3 is 9, so 11. 1 times 4 is 4. 3 times 5 is 15, so 19. Make sense? Okay. So now do the same thing with this second column here. So now we want to do 2, 3, 4, 5 with 2 and 4. Do the same set of operations with this one. Okay, 28. Can someone else check? Is that 1628 correct? Okay, Vidyut says 16. 28. Okay, so 1628. So since two of you said, I will just write it down as 1628. So now what we are saying is the result of multiplying this matrix with this matrix is this new matrix. So if I multiply 2, 3, 4, 5 with 1, 2, 3, 4, I get 11, 19, 16, 28. So all I did is I first took the first column, applied that to the first vector. So sorry, I took the matrix, first matrix, applied the transformation to the first vector inside this. Then I applied that same transformation to the second vector inside this, and I ended up getting these two. So that's all I did. So when multiplying, you split up columns and multiply vectors. Exactly, that's all. Would you add the 11 and 16? No, really, because these are two different vectors, right? 1, 3 is a different vector, 2, 4 is a different vector. All this is saying is if I had enough vectors, I'm going to just tell you where the vector 1 and 3 lands up under this transformation, where the vector 2 and 4 lands under this transformation. That's all this is telling us. When you multiplied a matrix with a vector, all you knew was where this vector is landing. That's the same idea, because I'm stacking up vectors doesn't mean anything changes. So I can even do this, right? So if I had 2, 3, 4, 5, if I had to multiply 1, 3, 2, 4, 5, Bad idea. 5, 6. If I had to do this, what would I do? Would the answer be 27, 47? No, it's not 27, 47 because vector 1, 3 resulted in vector 11, 19. So 1, 3 went to 11, 19, 2, 4 went to 16, 28. They are not going together, right? They are two separate vectors. They are going into two separate places. So answer is just these 4 numbers. So now try this one. So now I'm applying one transformation to three vectors. So what is the result? You should get 3 columns here. Obviously, the first 2 columns are the same, 11, 19 and 16, 28. What is the third column? So this is where this one landed, this is where this one landed, and this is where this one lands. So where does the point 5, 6 land under this transformation 2, 3, 4, 5? $28.50. Okay, anyone else can confirm that? Okay, so which would you multiply 5, 6 to? Always the same thing. So right, like Shruti. So ignore the other part of the matrix. It's just 2, 3, 4, 5 multiplied with 5, 6. So in this case, you would multiply 5 with 2 and 4, 6 with 3 and 5, right? Because this first column goes with this first value, second column goes with this second value. So you would multiply 5 with 2, 4 and 6 with 3, 5. Make sense, Shruti? Okay, cool. So this gives us 2850. So this is all matrix multiplication is about. Now let's look at how to do matrix inverse. So what's an inverse of a matrix and why is it important in solving linear equations? You remember how to solve this equation? What is y? 4. Okay, so all of you know how to do this. Now with matrices also, last time we saw this idea. So this is our real idea, right? Like we are saying a matrix A is, all it tells you is this vector x is going to this position B. Exactly. So we need to know x equal to A inverse times B. But how do you calculate A inverse? So for a given vector A, we want to calculate A inverse. When I say A inverse, what I'm really hoping is once I calculate this A inverse, I end up getting my original transformation, right? So I initially started a paper, I rotated it, right? And I stretched it. Now the inverse should kind of say, okay, first shrink it, then rotate it back in the opposite direction. That's what my inverse should say. And what should this result in? Because I initially started with the point 1, 0 and 1, 1. I started with these 2 points. I started with the points 1, 0 and 0, 1. I applied transformation A to this, which resulted them in being somewhere 2, 4, 3, 5. Exactly, yeah. So Prince got it. So it's, instead of getting 1, you should get back your original starting unit vectors, right? So you should get back your original starting unit vectors. So if you started with a point, you should get back to that original point because A, that's all A represented, right? A represents where did my initial 1001 go. So if I go and multiply this with its inverse, I should simply go back to my initial starting point, right? Does it make sense? Okay, cool. So now let's look at this equation. So 2, 3, 4, 5. And we don't know what are here, so I'll just call them A, B, C, D. I'm supposed to multiply these two matrices and get this 1, 0, 0, 1. How did it become 2? No, it didn't become Vidyut. That's just an example. Some transformation took 1, 0, 0, 1 to 2, 4, 3, 5. Right? That's some transformation. I don't know what it is. That's the transformation. Right? That's the example. So what should you multiply this with so that you get back your original point? Let's see what is that. Okay. So actually, let's first do it with numbers. So what is this first set? So A multiplies 2, 4, and B multiplies 3 and 5, right? So that's 2A plus 3B and 4A plus 5B equal to 1 equal to 0. Isn't it columns? Yeah. So ACBD, what's ACBD? What is ACBD here? Oh, you're telling me what is the inverse of a matrix formula. Is that what you're telling me, Prince? Oh, 2A plus 3C, is it? Yeah. So maybe, yeah, sorry. This is C. Yeah, you're right. 2A plus 3C, 4A plus 5C. Thank you. Right. So this is two equations. And then I take the same thing. I do B with 2, 4 and D with 3, 5. And I get 0, 1. Right. So that's 2B plus 3D equal to 0. And oops. 4B plus 5D equal to 1. Now, do you know how to solve these two equations? You can use elimination or substitution, right? Whatever. So let's solve them with elimination. So we multiply the first equation by 2, 4A plus 6C equal to 2, 4A plus 5C equal to 0. So subtracting these two gives me C equal to 2, right? Yeah, system of linear equations. So I'm just solving them. Now I substitute this back in this. So I get 5C is 10. So A equal to minus 10 over 4. So I solved for my first two things. So my A and C are solved. Then I'm solving for 2B plus 3D. So multiply the same, this one with first one with 2. 4B plus 6D equal to 0. 4B plus 5D equal to 1. So I subtract this, I get D equal to minus 1. Substitute that back into this, I get B equal to 5 over 4. Makes sense? So now I'm claiming my inverse. So my matrix 2, 3, 4, 5's inverse is equal to A was minus 10 over 4, B was 5 over 4, C was 2, and D is minus 1. So it's this. So this is my inverse. And that's all it is. It's not like some fancy thing or anything. That's it. Now, the gender, is this clear? Like how we calculated the inverse of this matrix? Does anyone have a question? No. Okay. So let's start from here. I wanted to calculate the inverse of this matrix, right? 2, 3, 4, 5. I'm saying the inverse of this matrix is some ABCD. I don't know what these ABCD are, but some ABCD. Okay. The meaning of applying a transformation and its inverse means my starting points 1, 0 will just come to 1, 0, 0, 1, right? Is this clear, Meena? Is this first equation clear? Okay, so do you understand what this is doing? First of all, when I say this matrix 2 3 4 5, what is this matrix 2 3 4 5? What does this even represent? What this represents, right, is the position of my initial vector 1 0, right? My unit vector along x-axis went here. My unit vector along y-axis went here. That's what this matrix represents, right? Is that clear? Okay. So what I'm saying is, if I multiply this with its inverse, which is ABCD, so imagine taking a paper, stretching it. So I have this, can I stretch something here? Okay, so I stretch this paper, right? Now, if I apply its inverse, wouldn't it be 6 by 4? We'll see that with you. If I apply its inverse, I would get it back, right? So I would get my original points back. So if I take the, if I first multiply with a matrix, it's all the stretched version. If I shrink it, then it's the original version. So if I do it right, like this is 100% to that. So this is the result. So my initial starting point should just come back, right? I should just come back to my initial point, which is 1001. Does that make sense, Maida? Okay. So what should A, B, and C, D be so that this result happens is what we are trying to calculate. That's what is the inverse of the matrix. And to do that, first what I did is I took this matrix and found out where the point AC would land. The point AC would land at 2A plus 3C and 4A plus 5C, right? So I'm saying that would be at 1 0, because after all the transformations are done, that should land at 1 0. Oh, did I make a mistake somewhere? Okay, let's check. So I started with 4A plus 6C equal to 2, 4A plus 5C equal to 0. So C equal to 2. C equal to 2 should give us A equal to minus 10 over 4. So that seems fine. Let's see the next one. Minus 4B minus 5 equal to 1. Yeah, absolutely. You're right. So 6 over 4. Sorry. So 6 over 4 is this one. Okay. So all I did, Meda, is basically I'm assuming that, okay, I'm applying this inverse and I should have resulted in my original point. And I'm going and numerically performing those operations, which we already tried. When I multiply this matrix with this matrix, I first multiply this matrix to this column, this matrix to this vector, and I should get these two vectors. So that's what I did here. First, I multiplied A with 2, 4, C with 3, 5, and I got 1, 0. Then I multiplied B with 2, 4. Then I multiplied D with 3, 5, and I got 0, 1. Then I went and solved these two linear equations that I got using elimination. And I found that this is the inverse of this matrix. Okay. Does that make sense? Okay. So this is the general direction along with you can go. So if I had a matrix A, B, C, D, what would its inverse be? So let's say my inverse is alpha, beta, gamma, delta. After multiplying, I want 1, 0, 0, 1. Okay, you can try this by yourself, but it is simply alpha times AC plus gamma times BD equal to 1, 0, and beta times AC plus delta times BD equal to 0, 1, right? So that's alpha A plus gamma B equal to 1 and alpha C plus gamma D equal to 0. From the first one, now if I have to get these two same coefficients, I'll multiply the first equation with C and the second equation with A. So I'll get alpha AC plus gamma BC equal to C. And then I'll get alpha AC plus gamma AD equal to 0. Subtracting these two, this gets cancelled. So I get gamma times BC minus AD equal to C, right? So my gamma is C over BC minus AD. So I found out my first point. All I'm doing is doing the same thing that we did with numbers, just with letters, so that we'll find out what's the general solution for a matrix inverse. Now I substitute this back here. So alpha C plus C over BC minus AD times D is equal to 0. So alpha C equal to minus DC over BC minus AD. And then alpha equal to minus D over BC minus AD. Does this make sense? So all I'm doing is I'm finding out the values. Can you try for me for this second pair of equations, beta AC plus delta BD, and tell me what happens? So I'll write down those here. Beta times AC plus delta times BD equal to 0, 1. Can you find out what the values of beta and delta end up being? Is someone trying? Is anyone trying? Okay, cool. So I will also try as you guys do that. If you guys finish before me, or if you guys, as you guys finish, you can write. I'll just I'm also doing it as along with you guys. If I make a mistake, you can point out also. Actually, I'll pause sharing for a second so that you guys can. How can I pause sharing? It's not easy on the phone. Okay, I'll stop sharing. Okay. Okay. Accidentally pressed enter. Okay. Gamma equal to. We are already done with gamma, but okay. A by AD by BC, AD minus BC. Which one is that? Okay. Yeah, sure. That's delta, I think, but okay. I'm very poor with these symbols, maybe. Yeah, that's absolutely fine. But yeah, that's the right answer. So minus A by, yeah, A by AD minus BC. Yeah, sure. What is the last one? So you just have one more left. Yeah, I can explain after the class is done with you. This is just more of just B by BC minus AD. Okay. Okay, cool. So now that you guys finished, I can share screen. Oh, harder to share screen than I thought. Okay, first go here. Okay, share screen. Okay. So we ended up getting these values for beta delta. So what we got is actually for our initial matrix, let me make the thickness little small so that I don't write just. So for our initial matrix A, B, C, D, we got this inverse matrix where alpha was minus D by BC minus AD. Beta was plus B by BC minus AD. Gamma was C by BC minus AD. And delta was minus A by BC minus AD. So this is our inverse. So if I multiply these two things, I'm going to get 1001. So that's where the difference comes from. All the terms are over the same denominator. Absolutely, yeah, Prince got it. So when you calculate the inverse of a matrix, you commonly see this formula which says 1 over either you can write it as AD minus BC or BC minus AD. It doesn't matter as long as you keep all the minus signs correct. 1 over BC minus AD times minus D plus B plus C minus A. You can write it like this, or in the more traditional format, which is 1 over AD minus BC. I'm multiplying everything with 1. So this is D minus B minus C A. These two are of course equal because I just multiplied with minus 1. Does this make sense? So this, for my given matrix A, this is the inverse. And nothing fancy, right? All it took was like a few small steps, nothing magical or anything. Very basic linear equation solution that resulted in this inverse of a matrix. But using our original intuition that all a pair of linear equations are doing is a set of linear transformations, that's our original intuition. From there, we can use this to solve any linear equations. That's what it ended up being. I'll just introduce one more concept before we go any further. And that's the idea of, oops, I didn't mean to do this, but okay. So is this clear? Like, so this is all a matrix inverse is. So given any two-dimensional matrix, like 1, 4, 6, 7, you can just plug in these numbers. So you multiply this diagonal and subtract. So 1 over 7 minus 24 times, you flip these two values, 7 and 1, and you put a negative 1 before these values. So this is minus 1 over 17, 7 minus 6 minus 4, 1. This is what you probably would have learned somewhere. If you have already learned matrices, matrix inverses, you probably are familiar with this method, right? I don't know if some of you are familiar with this already, but those of you who know, you might have seen this already. But this is why it came there. My motivation was to show why, not how, or how and not how to do. Does this make sense? Okay, so what we looked in this class is matrices as linear transformations, matrix vector multiplication is just equal to where does the vector land, after the transformation, and matrix multiplication is where does vector land after two transformations. And matrix inverse is the transform that brings original unit vectors back to place. So this is the intuition or math behind this. We'll just look at one more concept, which is actually very useful in solving, not solving linear equation, but in linear algebra in general. It is the idea of, so we initially started with this idea, right? Like this is the initial unit vectors. This is 1, 0, and this is 0, 1. Under some transformations like this, I hope I could rotate this. Is there? Oh yeah, I can rotate this actually. I should have done this on my phone rather than paint from the beginning. So I start with this. I stretched it. Does my phone let me rotate this thing? No, not very easily. No, stretching worked fine. Nope. I was hoping I could just rotate this nicely, but doesn't look like I can easily do that. No, okay, too bad. So this is just the stretching part of it. And then you could also rotate it if you want, right? I could rotate this one if I want. So under these rotations, what happens? It's stretching rotation. Of course, you can also do translation, right? Which is, if I stretched and rotated to here, I could also do this. Get rid of my initial lines. And this was probably my final line. So this is my new axis, right? So my original axis was this. My new axis is this. This is where my origin is still. So under this transformation, whatever happens is what we saw so far. Now, this is very hard for me to draw. I don't even know how to draw. I'll give you like some YouTube videos where you could probably watch this. If I find some good ones, I'm sure I'll find some good ones. The idea is of a Eigen vector. Has anyone heard of this already? Like if you have not, if no one has heard, then maybe I'll just skip and we can talk about it somewhere later. Okay, you have already heard. Okay, whoever has heard already, what's an Eigen vector? Aditya Jain, Arakshata Tiwari, what's an Eigen vector? You can speak, you don't have to type. It's like a non-zero scalar change. Non-zero scalar change. What does that mean? A vector is not a change, right? It's kind of like a vector that changes by a scalar factor when a linear transformation is applied. Absolutely, yeah. So for a given set of transformations, so let's say I start with this axis. And I have this initial vector, whatever this is. I don't know if this is the good vector, but let's say I have this vector. And somehow after I rotate and stretch and translate whatever I did, if I ended up with, in my new axis, if I ended up with this vector, which still looks almost identical, right? So if it's just this, but scaled, right? It didn't move anywhere. It's still in the same direction. When will the homework cover be updated? I don't know. Will update. So if you scale, if this gets scaled, all that happened is this initial vector just got scaled and nothing else happened. So it got stretched, but it didn't move anywhere. It didn't rotate. It didn't go anywhere else. These are eigenvectors. You already know of two eigenvectors always. What are the two eigenvectors that are always there? Anybody? Okay, what are the vectors that don't change when you stretch, when you just stretch a vector? If you just stretch the paper, what are the vectors that don't rotate anywhere? All of them, right? Like, so if the transformation was just stretching, nothing changed. All of them are still at the same direction or same place. But there are two special vectors in terms of which we have always been talking. These are the unit vectors, right? Like along this direction. Of course, they are rotating, but eigenvectors, what they give us is the advantage of talking about everything with respect to these vectors. Because they are not changing in position, you can talk about what's happening to all the other points with respect to these. When you did stretching and rotation, even the axis had changed, right? If you remember, the axis also changes. But if there is such a vector which doesn't change, then it would be convenient to talk about all the other things in terms of this vector, right? Does that make sense? So mathematically speaking, this is represented like this. So if this is our transformation, and let's say this is our vector u, this is just some scaled version of u. So we will call it like some ku. So if this is ku, these are vectors. So if we get this, then this is an eigenvector. So it's convenient to talk about everything else in terms of these eigenvectors. Nothing fancy, just the simple intuition that we built so far also helps in some other instances. Any questions? Okay, cool. When will the homework for the last two classes be updated? We don't know right now. We'll probably update today or tomorrow for at least for one of them at least. I don't know which one. We'll post the solutions, I think, today or tomorrow. Whenever the next set is posted, we'll post the solutions. You guys can check for yourself. We'll update the scores little later. Any other questions? Okay. If you guys don't have any other questions, this is all the ideas that I wanted to present in today's class, and we are almost at the end. If something is not clear, you guys can stay. Otherwise, you guys can leave. We'll post homework in a day or two. Homework will involve some programming, not just idea.
Thank
Okay,
you.
thank you.
Bye.
Thank you. Bye.
Bye.
Bye. Thank you.
Thank you. Okay. If no one has any questions, we can also stop. Of those who are could you please explain the basic multiplication of the matrices? Okay. So can you still see my screen? Navya, can you see my screen? Okay, actually you can speak so that I know what you're following or not following. So give me some matrix, Navya, it doesn't matter, some matrix. You can speak so that way I can understand where you are.
3, 5, 6, 2.
Like this, did you mean like this?
Yeah.
Okay, so when we say we are multiplying two matrices, what it means is, initially what did this matrix represent? Multiplying this matrix with this unit vector 1 1, right, resulted in something. So that's what initially we thought of as matrix and vector multiplication, right? Does that make sense, Navya? You can speak, yeah. So how did we multiply this? We said that this first column is where the point 1 0 lands. So we would just multiply that with 1 and 3 6. And this second column is where this second point 1 lands. So we would multiply this with 5 and 2. Is this clear how we are doing this?
Yeah.
Okay. So what do you get when you do this? You get 1 times 3 plus 1 times 5, 8. 1 times 6 plus 1 times 2, also 8. Very convenient. Interesting. You picked a nice matrix. Okay, so now if we were multiplying two matrices, a matrix with another matrix, what that really represents is this second matrix, you can imagine this as two vectors. So let's say we have this vector 1 2 and this vector 3 4. So you can divide this matrix into two pieces and first multiply this with this vector, then this matrix with this vector. So you start with 3 5 6 2 and multiply 1 2 and start with 3 5 6 2 and multiply 3 4. Does this make sense?
Yeah.
So how do you multiply this 3 5 6 2 with 1 2? You multiply this column with this column with this, right?
Yeah.
So what do you get when you multiply 3 6 5 2 with 1 2? What do you get?
You get 9.
Okay, let's check. So you get 1 times 3 6, right?
Yeah.
This 1 times 3 6 plus 2 times.
5 2.
Okay, and what do you get?
You get 9 and 14.
Now the way this goes is, you're supposed to multiply this 1 to this 3. So you get 1 times 3 as 3. Then you're supposed to add this 2 multiplied with this 5, that's 10, right?
Yeah.
So then you multiply this 1 to this 6, that's 6. Then you multiply this 2 to this 2, that's 4. So you get 13, 10, right?
Yeah.
Does that make sense?
Yeah, it does.
Now try the same thing with 3 and 4 here. So you multiply this 3 with that 3. Can you
it
try?
would be 9.
Okay. And then what do you get? Let me erase this part. So you multiply that first one was 9. Then what?
20.
Okay. Then what goes in the second row?
18 and 8.
Okay. So you get 29 and 26, right? I just added 9 plus 20 and 18 plus 8. So
Yeah.
the result of multiplying these two matrix 3, 5, 6, 2 and 1, 2, 3, 4. Did I write them right? Yeah. Okay, 1, 2, 3, 4 is this new matrix where the first column is 29, 26. The second column is, first column is 13, 10. And the second column is 29, 26. What this means is, if I took this first point, which started at 1, 2 and 3, 4, these 2 points, and I applied this transformation, they will land at 13, 10 and 29, 26. But this itself means I started with 3, 6, 5, 2, 1, 2, 3, 4 and 1, 0, 0, 1, right? I started with my unit vectors and this is where my unit vectors landed up. That's what this really means. So I started with my unit vectors in this direction, these tiny lines. First I did something that made them go to where is 1, 2 here and somewhat here. So it made them go here and here. Okay. So after I did something, this line went here, this line went here. Then I did another thing which took them to 13, 10 would be somewhere here. And 29, 26 would be far away from this, somewhere here. So they went here. So my first line, let me try a different color. Maybe it will be more obvious. No, somewhat different color. Okay. So my line here went initially to this and then to this. After I multiplied with two matrices, it just landed up here. That's what matrix multiplication really does.
Thank you.
Is this okay? Cool. No, thank you. Okay, anyone else who is there still? Benjamin, Neha, Aryan, Akshata, Arham. Do you guys have any questions or did you just not close the session? Okay, looks like no questions. Okay, so Pavan, any idea when we can upload this course? I know I sent it late, but
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatrical.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!